In this problem, we're given two cyclic groups, G1 and G2, with the same product, and we're told that they have a common proper subgroup H, and the order of H is 7. Of G2, we also have the information that any other proper subgroup has order 3, right? Any other. And finally, we know that the size of the group G1, so the order of the group G1 is smaller, strictly smaller than the order of the group G2. The question is, what is the order of G1, right? Okay, seems a bit weird that we're able to figure out what is the order of this with this information that we have here, but it turns out that we have enough information because, and this is very important, these are cyclic groups, right? Okay, and this H is a proper subgroup, proper, which means that in particular, that the size of G1 has to be larger than 7, right? Okay, so we have this. Not only that, because it's a subgroup of G1 and G2, we know that 7 must be a divisor of the order of G1, and 7 must be also a divisor of the order of G2, right? Okay, so it's a common divisor of both, and it's a proper divisor. All right, let's focus on G2 because we have more information about G2. We have that for now we know that 7 is a divisor of this, so the order of this has to be 7 times something. And now we know that all the other proper subgroup of G2 have order 3. So 3 must be also a divisor of this, right? Suppose that the divisor is 3 to k, right? Well, obviously there are no other divisors than 7 and 3 because the only proper subgroups have order 3 and order 7. And because they are cyclic group, we know that for every divisor of the order of the group, there is a subgroup. So this is a very important information, right? Now suppose that k is larger than 1. So for instance, take as an example that k is equal to 2, right? And then the order would be 7 times 3 squared. Well, if this is true and G2 is a cyclic group, it means that it should have a proper subgroup of order 7, that's okay, is H, of order 3, okay, we're told that all the others have order 3, but also of order 9, because 3 squared is a proper divisor of this, and of order 21, which would be 7 times 3. And this would be all proper divisors, and therefore they should have, G2 should have a proper subgroup for every one of them. One at least, right? But we're told that all the other subgroups, apart from H itself, have order 3. So these are excluded. So the only possibility is that this is power 1. So actually, we know everything about G2. We know that the order of G2 is 21, right? So it's got only 2 factors, 7 and 3, and there are subgroups, proper subgroups of order 7 and order 3, and no more, right? Okay, finally, we know this. We know, because of this, we know that the order of G1 has to be 7 times m, for some m. M has to be larger than 1 because 7 has to be a proper divisor, right? But on the other hand, we know that this has to be smaller than 7 times 3. Okay, which is the order of the group G2, sorry. So that implies that m has to be smaller than 3. So it has to be larger than 1 and smaller than 3. So the only possibility is that m is equal to 2. Therefore, G1, the size of G1 has to be 7 times 2, and it is 14. So the order of the group G1 has to be 14, given all these pieces of information.